I'll go ahead and get started. So we're gonna look at an entropy balance. I haven't screen shared yet, but we're gonna look at one for the Brayton cycle. I just wanted to make sure that everybody understands what we got going on with that. I'll look at the compressor, and then I'm sure you have worked it. I don't know what y'all have done and what y'all haven't. Okay. Do I want to do it like that? Yeah, sure. So we have the compressor. It's compressing air this time since the fuel is coming in later. It's going through this little, I guess, a combustion chamber. And then it's getting expanded. Alright, and that's what we're going to try to find. We're going to try to find the work of that compressor, just based off of what we're given. And we're given that the air is at, 310, okay? Yeah, that's right, okay. So this is air at 310, and it's at atmospheric pressure. It's the air from the surroundings. So P equals 1 ATM, or whatever that is in PSI and kPa. So I'm going to look at the entropy balance. I mean, we've done enough energy balances that I can just go ahead and write it out. I mean, the work of the compressor is equal to, well, I'll call this 1 and 2. I'm not sure which numbers those are. Oh, wait, I remember now. I think it's 12 and 13. Correct me if I'm wrong. So it'll be in. So what's going to be the energy balance? I'm writing this out first, and then I'll go to the entropy. Equals DH equals because it's just going to be CP dt, and then there you go. Bam. You have your stuff, except you don't have T13. So that's the problem. You don't have T13. And you don't have work. So you have two equations and one unknown. Sorry. One equation and two unknowns. And so you need to have another equation, and that other equation is going to be your entropy balance. Where in this case, it ends up, since we're going to first assume that it's reversible and then use the isotropic efficiency. Reversible, or I'm not going to write reversible because it's technically not. That's just how you figure it out. So ideal work, I should say, ideal work, or not work, just ideal, because there is no work in the entropy balance. And you end up subtracting that out. I mean, doing some math, and you take away the mass. And then this goes to 0 because it's reversible. And then you can find the the temperature using this. And in this case, since it's, again, because ideal gas, you can write out an equation that I need to look up again because I always write it down wrong. Okay. And so this equals Cp over T minus RP dP. Okay. And so we can rearrange this if we integrate from T12 to T13. Now we can actually solve for T13 ideal. This is also ideal. T13 or S ideal, because we're assuming that it's reversible. That integral goes to 0, or this whole integral goes to 0. And pressure is always going to stay as a not real. We don't really typically assume that pressure changes from real to ideal cases. So we're just not going to, this is already, technically, this is real, but you don't need to write that because it's already there. Okay, and then you can rearrange all this. Actually, I'm not going to rearrange all this because then that would mess up this integral. So what you would do here is you'd have the A plus BT plus CT squared plus all this over T dt, and then you'd integrate that, and then you'd integrate this, and I'll just say that R will say what this is already. I know that yeah, okay. Never mind. Forget that. P13. Yeah, that's right. Okay, so, and this is all equal to 0. Okay, so if you take this integral, you can solve for T13. So this will be what it will be. I'm gonna take the integral. Just go ahead and do it. Okay, so I'm just going to do this part and then I'll add this part later. So taking the integral, if I can remember how to do that. It's the A times the natural log of T13 over T12 plus B times T plus CT squared over 2 plus DT to the negative 2 over, over negative 2. Correct me if I'm wrong. Pretty sure that's right. Okay. Actually, I should just say that this is the natural, because I haven't done the limits of, this is from T, so the natural log of T, right? Yeah, and then I'll, not T anything, just T, okay. And then I'll bring this down later again. And now I'll subtract it out. So now it's A times the natural log of T13 over T12. I'm just making all the math easier. So T. I mean, not writing it down, I mean. If only I could make it easier. That'd be nice. Let's do this. All over -2. All right, then you use numerical integration, and you solve this for T13. Simple, and you're done. All right. So then you have your T13 ideal. Okay. So you can then, once you have your T13 ideal, you can use that in your work at the your energy balance up here for this part of it, where you'd have A plus B, well, from the integral of T13 or T12 to T13. So you plug in your T13 ideal to find your work of the compressor ideal, and then once you take that integral, do all that stuff for, in this case, very specifically, this is for air. I'm just going to remind you again, it's for air. You find the work of the compressor real by taking the work of the compressor ideal and dividing it by its isentropic efficiency. I think I told you on the before that to multiply it, but that doesn't make sense since you're adding work and it requires more work to power the compressor than you expected. So dividing it by the isentropic efficiency just makes more sense to do, or is the correct thing to do. So then, oh yeah. Yeah, I told y'all that it's equal to 0.92, or at least I think it's 0.92. Yeah, no problem. I'm just going to check. Yeah, 0.92. All right, and then you just backtrack it again. So this time you know what the work of the compressor real is, so you can just use the energy balance again to solve for T13 real. And that's what I really want here. CP dt. Okay? So then you solve for T13 real. Okay? You do the same thing on that turbine, just the other way around, where the work of the turbine real equals the isotropic efficiency times the work of the turbine ideal. And this is all bar. I don't know. I'm not writing bar, but you'll get that. There might be time to go over how to scale up today, if there's no other questions, if everybody's already ready there. Or I don't even know. How many of y'all have already scaled up? Okay. Gotcha. Are there any questions on what I just did? Wait, what happened? Did all my work just go away? No, okay, there we go. Excuse me. All right, good. There's no questions on what I did. That's good. That's good. Okay, so I did get a question about whether or not you'd include partial pressure inside of this this entropy balance, where you have this, and since like we're dealing with a multi-component, so like air is a multi-component, so we have O2 and N2, and I might have questioned myself on this. Whether or not you would have partial pressure inside of this P. And the answer is no, you wouldn't. And that's just because we're not dealing with the entropy of mixing. The entropy of mixing is whenever you assume that things aren't well mixed. And it's just kind of obvious when you say it out loud. But whenever stuff isn't well mixed, you deal with this term, and that involves partial pressures of each component, and that becomes important whenever you don't, whenever you are dealing with valves, and where things expand really quickly but also liquefy at the same time. So you don't know what kind of mixture that you end up with at the end. While in this case, you just have all gas, and you assume that we're assuming that all of the particles are distributed evenly, therefore well mixed. And that doesn't matter whenever we're dealing with. And partial pressure doesn't matter whenever we're dealing with normal entropy. I'm not sure why it doesn't matter, but I just know it doesn't. I don't know if Dr. Griffith has already started talking about entropy of mixing. He might soon. I'm sure we'll get there if we ever, finish the semester. But that's all. I just wanted to mention that. And then I could go ahead and show you. Maybe I'll show you this girl. I don't know. Let's see what I can do real quick. Okay. So let's just say we have all the works for each thing. So we have the the CO2? No, inside the heat exchanger, it's from T. Well, it's from like all of them. So you kind of have. Let me get my thing out real quick. So, can y'all see my mouse? Or is it glitchy? Okay, cool. So, inside the heat exchanger, or the combustion chamber right here, it's from T13 and T14 to T15. So, because these are coming in at different temperatures again, just like it was over here in this one. So we'd have in this combustion chamber, we'd bring our temperatures to some reference temperature and find T15, just like we found T3, T out of that combustion chamber. Just we're going to be using different temperatures this time. I mean, it's the same math. You could actually even copy and paste what you already did for this one into another cell if you have it set up the right way. You could just copy and paste it and roll into T15 like real easily. As for probably gonna need to take a look at that again. But okay. As for finding the scale up works. So I'm gonna go ahead and say that, like, this is the Brayton cycle. This is the work of the turbine and the Brayton cycle. This is work of the compressor. So we also have the pump. It requires work. And then over here we have another turbine. Okay. So let's just say that we have all of those numbers. Let's say that, let's just, for arbitrary reasons, I'm not sure what they are. I'm just going to say that this is 62 kilojoules per kilogram of, no, per mole of fuel. Okay. And, oh, whoops. Okay. And this is like, I don't know, 300. Why am I saying 62? I'm just going to go with 60. Nice. Good numbers. Oh, all right. And then this is 50. Except this time it's in kilograms of steam because it's inside the Rankine cycle. And we'll just go with as 400. All right, that's the only time I'm going to write the units down for that, but you'll know what's what. All right, so our work net is equal to 300,000 kilowatts, or 300 megawatts. And so what we did inside of those heat exchangers was we found the mass ratios between mole of fuel per kilogram of steam. And so if I take my work of the compressor in the Brayton cycle and the turbine, I can multiply by this ratio. Let's say that this ratio for, okay, hold on, I'll show you. For this heat exchanger that's right here, okay, this one, we're just going to say that it's, I didn't know I could draw on this Excel sheet. That's kind of cool. For this heat exchanger, for this arbitrary purpose, we're going to say that the mass ratio is 0.4, or 0.5, actually. So 1/2. Okay? So if I take my compressor, and I want it in kilograms of steam, so that way just everything's in kilograms of steam. So I'm going to take this 60, multiply it by 0.5, and now I have it in kilojoules per kilogram of steam. So, 30. Or actually, I'll write it. I'll keep it there. I'm sorry. 30. All right, and then the work of the turbine, same thing. It's going to be, that equals 150. All right, so now we have that all in kilograms of steam. And so what I like to do is say that I'm just going to add up all my works. And this is at the end. This is at the end process, so nothing's dependent upon whether or not these add up properly. So I'm just going to say that all of these are additive. Or this isn't. The work net equals the work of the turbine 1 plus turbine 2 minus the work of the pump minus the work of the compressor. Okay, and that's what all of them equal. I'm just going to say that that's how that would end up. Okay, and so what I can also say, not only that, I can also say that work net bar. Oh, this is all dot. These are all dots. Okay, work net bar is equal to work of the turbine 1 plus work of the turbine 2 minus work. All right, all that. Okay, and so now I can just add up everything. So what did I say those numbers were? It was 400 plus 300 minus 50, and then there was a 60. Okay. So we got 700, 650, 650 minus 60, 590. All right, so we got 590 what? Where? Yeah, you're right. My bad. Yeah, you're supposed to use that. Thanks. I didn't do pointless math for no reason. I just kind of whoops. So 50 and then minus 30. Yeah, thanks. Appreciate that. So that would be okay, 470. Okay. So now that I have that number, I know what my scale up number is. So I know that if I take my work net dot, manipulate it somehow. Hold on. Need to do what? What do I need to do? Divide it by. Is that right? Yeah. Yeah, that's right. Okay. Work bar net. So that ends up being 300,000 kilograms. No, kilowatts. Kilowatts over 470 kilojoules steam. Okay, so then you divide those two. Can someone do that math for me? And what you're left with is the mass of the steam. The mass dot of the steam. And that's in kilograms of steam per second. Cool. Is it 3 repeating? Alright, cool. That's fine. And this is just an arbitrary number. I was just curious. So this is equal to the mass of the steam, and that's how you scale up. Pretty simple how to scale up. I'm just wanted to show that to me. I think that's everything I wanted to show you today. Are there any questions based on what I have done? No? Yeah, I did get quiet. Actually, yeah, and then you can go around the whole system and use your heat exchangers to scale up or to find the other masses that you would need or moles that you would need to solve the whole process for how much each flow rate is across the whole system. Are there any questions on what I've done? Because I'm gonna go ahead and make this due on next Wednesday. Okay.